Hey, hi, I'm Sriram, and today I'll be presenting a work on shape from heat conduction. You might ask, why shape from heat, right? Because with heat, you can reconstruct objects where traditional light based methods fail, such as dark or transparent objects. But before we dig any deeper, let's first try to understand what differentiates light and heat. So, light transport refers to propagation and interactions of light through reflection, refraction, scattering, and transmission, along with some amount of absorption also happening in all these scenarios. It forms the basis of all shape from X techniques in computer vision over the past 50 years, from shape from shading, polarization, turbulence, and more. And recent advances have developed techniques to utilize similar light transport effects in the thermal wavelengths, for example, to do photometric stereo, shape from thermal radiation, and more. But in this world, we're not interested in modeling the propagation of light. Rather, we are interested in modeling the propagation of heat, which is fundamentally different from how light works. So, what is heat transport? The transfer of heat energy from one point to another is what we call heat transport. It can happen through one of three modes, namely radiation, convection, and conduction. Among this, conduction that happens through contact is shape dependent. For example, farther the distance between any two points, longer the heat has to travel, thus the shape dependent aspect. But one thing for sure is heat transport happens all the time. It happens wherever light can go and even beyond through movement of fluids and contact. Thermal cameras in this case can be a useful tool as they capture radiation emitted by an object in addition to the light reflected by it. And this emitted radiation acts as a conduit to the world of heat transport that we wish to leverage. While imaging an object illuminated with a light looks static in the visible, the thermal video shows how temperature propagates over the surface. An interesting thing to observe here is how heat conducts along the surface from the exposed regions to the unexposed sides. With this observation, we would like to ask a fundamental question in this work. Can we infer an object's shape by just observing its heat flow? To faithfully answer that question, we need to look at the underlying physical equation that governs this heat transfer process. In this energy balance equation, the change in temperature on the left at any point can be equated to the sum of energy absorbed, radiated, convected, and conducted by that region. And the shape dependent component in the conduction is a Laplace operator, which is shown here. By discussing the heat transport equation, we can write thermal videos as a system of linear equations where the unknown quantities are the heat capacity, the Laplace operator, the convection coefficient, and the absorbed heat flux. Solving this linear system across time will yield scene, material, and geometric properties without having to estimate or make any assumption about the optical properties, environment lighting, or how this object exists in the 3D space. Measuring the absorbed energy or other estimated quantities can already be useful in many engineering applications without the 3D geometry. But our aim here is to go one step further to recover the object shape from the Laplace operator. The estimated Laplace operator in its discrete form for a mesh with V vertices is a V cross V sparse matrix. One can extract edge lengths of a triangular mesh with the information encoded in this Laplace operator. But there can be different 3D shapes which satisfies these edge lengths. This makes shape recovery from the Laplace operator inherently ambiguous. But having points in the 3D space constrained to the camera ray reduces this possible isometric deformation to locally binary. We address this local binary ambiguity using two uncalibrated light sources with insight that absorbed heat flux follows Lambert's cosine law, we constrain the normals in the mesh towards one of the half spaces in the x and the y axis. Using input thermal videos from these uncalibrated sources, we perform a coarse to fine refinement strategy, optimizing over object's depth to faithfully reconstruct both high and low frequency details of this textureless black bear. Since SFM and other reconstruction methods fail with such objects, we paint the object with textures and obtain ground truth shape. The sign distance error shows accurate reconstruction with a mean absolute error of just 1.4 millimeter. Okay, textureless objects are great, but the real advantage of these systems comes with the ability to reconstruct visibly transparent or translucent objects. While ability to emit infrared radiation can vary between different materials, these objects appear opaque in thermal, allowing one to perform reconstructions which otherwise might not be possible using a visible camera. To demonstrate the fact that heat transfer can be induced more broadly compared to light, we ask this question. Can we heat up objects in other ways and still reconstruct its shape? To answer the question, we heated an object using a hot air blower and ran our optimization routine to reconstruct its shape. The subsequent reconstructions show intricate shape details that we recovered even in the case of transparent glass objects. But is heating up an object always necessary to recover shape? We captured a video of an object naturally cooling down, indicated by the temperature plot on the right, and our optimization results show that shape recovery is still possible in this setting. Because both heating and cooling are heat transfer processes which disturb objects from their steady state temperatures and induce heat conduction. We perform reconstructions on a variety of other objects such as plastic bottles, 3D printed bunny, and colored bear. For more results, please check out our paper on our website. To conclude, heat transport is ubiquitous and much broader than light transport. It happens wherever light can go and even beyond through movement of fluids or contact. Objects that are dark, transparent, or translucent in the visible can be reconstructed in thermal as they have complementary BRDF characteristics. As energy can neither be created nor destroyed, light lost through absorption in the visible can heat up an object and still be useful, showing up as emitted radiation in the thermal spectrum. Finally, using emitted energy as a conduit to the world of heat transport opens up exciting research avenues that make thermal infrared an interesting study. Thank you.